Okay. Once you get this open, you can create a new fluent. Right-click on geometry, new to modeler. Once you get into this, you want to click into the XY plane. You want to sketch a circle. Then you want to sketch a rectangle around it. You go to dimensions, define all three of these. And then you want to center it. Okay, and now we can go to concepts or some sketches. Apply and generate. And then we can create a new sketch. I'm going to sketch a rectangle around there. And then we're going to go to dimensions. Okay, and then we're going to general dimensions to define a rectangle. Okay, that. Okay, at this point, just draw that line. Vertical line, vertical line. Okay. Let's hope it works this time. Okay, that's good. Okay. Yes, I realize what I'm doing wrong. It's kind of a dumb mistake on my part. We need to do a face split. Okay, that's fine. Okay. It's good. Now we go back to our image, update it, and then we can open Mesh. Okay. If you do not see these lines, then you always need to go back, and the face split is usually the problem. The first thing I'm going to do is I'm going to start naming things. So go to select create name section. This would be inlet. It would be nice if we can put a line in there and then split that in half. Let's see how that works. Let's go back to geometry and then add a line. Through here. Let's see if that works. Let's try to edit the face split. And if that allows me to edit the face split. Yeah, let's get out of that. I believe that is working. It's only working on one of them. Or there, I just missed one. Okay. Let's go to this and re-update that. It's probably going to give you an error. Okay. Okay, I assume this will now be this surface. Okay. It should be alright, because that would be the non-slip condition. I'm actually kind of curious where let me select those. Perhaps I'm too far out, so it won't. Okay, yeah. Just in case, let's do that. Okay, now let's insert sizing. 50. Okay, so I don't know if that would create a problem. I guess we'll find out. For some reason it likes running through that. It's important to wait until it's done meshing, otherwise could create a problem. So face meshing. Actually, to exit out of that, let's see if we can create just name it flow area, see if that works. I guess I'll just delete that and create a new face mesh. Okay, that does not work like that apparently. Why will it not allow me to create and Okay. Trying to preview the mesh, but it's not allowing me. Okay. Well, let's just see if it worked. Okay. Since we have completed the mesh, let's duplicate this twice. Okay. Now let's go to setup. We will start with a turbulent flow. Since I have an older computer, it takes a while to load, but just gotta be patient. Okay, viscous laminar, correct, okay. Next, we want to go to fluid and set the density. Let's do 1.2 for the density, and 1.8 for viscosity. Let's go to boundary conditions for the inlet. Let's do 8 meters per second. Okay, that's good. The outlet, let's do a back pressure. Oh, first of all, yeah. Okay, that's good. Make sure the symmetries are type symmetry. Yes, that's correct. Let's check the surface of the cylinder. Should be non-slip. Stationary non-slip. Yes, that's correct. And then try this one too. Yeah, that's correct. Reference values should be from the inlet 1.2 and 1.8. Yes, that's correct. Okay. Let's initialize it. Actually, do a plot. Just gonna size it first. Let's do 30. Just go to 30. Then you can run calculation. Don't set it too high. For example, I set it at 100,000 the other day accidentally, and it took forever. So just wait until that's done. Okay, that's good. create an XY plot for pressure and then pressure coefficient. Let's see if we can do it on the surface of the cylinder. Okay, that is not, it's not working very well. Okay. Okay, that's very interesting, actually. Alright, so let's move on from that. That would definitely not be correct, but let's go to results, see if we can get it in a different format. Okay, let's create two lines on top of the cylinder at gotta see if that's in the correct spot. Okay, it looks to be in the correct spot. Location line. Let's just go from 0. Okay, let's enter its chart. For this one, we will do the velocity variation data series. Let's include let's just keep it series 2. Series velocity u and y. Okay, and create a screenshot of that. Okay, and let's change this to get the pressure. Okay, there's the pressure variation. Okay, then let's plot contours. So exit the chart. Enter contour 1. Let's name it. Okay. Inlet, let's do velocity U, global 110. Apply, preview. Let's see why. Maybe it's all good. Velocity U, strike pressure. Yeah, so G1 actually. So let's do velocity 1 first. Velocity U. At symmetry 1. Okay, you can tell something is off. So it should be symmetrical on both sides, but instead it looks like the flow is only going above the cylinder, which is very strange. Perhaps this is enough turbulent that it created a specific flow. Perhaps. And let's just assume that for this case. Okay. Okay, let's create pressure. Okay, that does look correct this time. So it has an area of relative low pressure after the cylinder and very high pressure at the start of the cylinder. So yes, that does look good. Okay, screenshot that. Okay. Now let's look at the streamlines. Let's see. Actually, yeah. One minute here. Can I have a four? Please. Okay, geometry equals space, symmetry 1. Let's see if that works. Okay, my computer is very slow. Thank you. computer is very, very slow. %, 100%, okay. So it should be almost done if it's at 100%. Okay, that is a very interesting velocity streamline. And as you can see from this velocity streamline, it appears that the inlet velocity is only applying at the top of the cylinder, which is clearly incorrect. It should be on both the bottom and the top. But since it is like this, it is cool to see how it creates a spiral pattern with the flow. Okay, that will be all for turbulent. Okay, now we will be doing laminar flow. Okay, let's go to setup and start it. Okay, so when we did turbulent flow, 8 meters per second correlated to a Reynolds number of 533,333.33333, which is greater than 500,000, resulting in turbulent flow. So if we half that to 4 meters per second, then it would be less than 500,000 and will be laminar flow. Okay. I believe this is the object that was messing up last time. However, I do not know how to remove it in this instance. Let's try to do it as an interface, see if that removes our problem. If not, we might have to change it a little bit. Okay, reference values, impute from the inlet, 1.2 and 1.8, yes, that's correct. Now we want to initialize. It should be 20 to 30 iterations. Initialize that. Okay, yes, the interface zone is giving a problem. So, do have to change the type. Let's try it as a symmetry, see if that removes our problem. Okay, so that should work. Let's run the calculation. Let's do 50 iterations this time, just to save time. Okay, 50 iterations later, that works. So let's try to do the plot. It did not work for turbulent, however it is worth trying for this one. Shear coefficient around the surface of the cylinder and the top surface of the cylinder. Okay, that is creating very skewed results, so I will assume this still will not work in that mode. Okay. So I want to go to results. Okay. So we will create our lines above the cylinder. So line 1 will be at -0.5, -0.5, up to 3, 110, 100. Location. Line 2 at 0, 0, to 3. And this would be a 0.5, 0.5, up to 3. Okay, so now we will create a chart. This would be for the velocity variation. Line 2. And line 3. Okay, so this is showing very low pressure at the end of the cylinder. Okay. This one is for velocity u. Okay, that looks a little bit better. Okay. So actually we will change line 1 to start at 0.5. Because the other information is not very helpful. Okay, that's good. Okay. And then go to chart 1 and we can change that to pressure variation. Change it to pressure. Okay. Okay, let's create a pressure contour from symmetry 1. Okay, that is showing what we want to see. Create a screenshot of that. Okay, and now we want to exit out of that and create a velocity contour. Okay, it appears that again the inlet flow is only above the cylinder for some reason. Okay, and now we want to do the streamline. Okay, it's almost done. Again, the results are very skewed, which makes me very frustrated. That is not what it should look like. However, this program does not like to function correctly when I am recording for some reason. Okay. That is all for the laminar. Okay. See if we can edit this flow a little bit. I'm just gonna try this to see if that will create a better result. It doesn't look like it did, so try another thing. Okay, that does not work, sadly. Okay, so this has been the problem with the inlet. The inlet should be this whole area. That is very frustrating. It's okay. So I will go back. Okay. So this inlet. We're actually gonna have to update it. Okay. So we can start this. This grid is taking a minute to load, which is a little bit annoying. But, I mean, it's good to have a little bit of break. Okay, viscous laminar. So this will be inviscid flow. So basically you want the dry coefficient to be close to 0. 0.008 perhaps would be a good number. And then to get that, you want a very low Reynolds number. So I will change boundary conditions of the inlet to, instead of being 8 meters per second like the turbulent, 4 meters per second like the laminar, I will try 0.05 meters per second. So again, that will bring the Reynolds number down, creating a almost zero drag coefficient. Okay. Check on the walls. And again, somehow that is becoming a non-slope condition, so I'll try to get rid of it with the symmetry. The outlet should be no reverse flow. And then we will check the density, should be 1.2. Okay, check the reference values from the inlet. Okay, that's good. Now we want to initialize. Okay. For the sake of time, we will do 50 iterations and calculate. Once the calculation is complete, we can either try an XY plot of pressure coefficient. Okay, good. It works this time. So there is the pressure coefficient plot. We'll take a screenshot of that. I hope I spelled that correctly. Inviscid flow, actually. This will be pressure coefficient. Okay, now we go back to Workbench and start the results. So we're going to create 3 laws. So one at the start of, actually, we'll just call it one. Later we should call it start of cylinder just so we know what it is. However, for now, this will not be shown, so it is up to your discretion what you want to do. Okay, so 2 more lines. That's 0, 0, 53, from 0.5. Five, 0.5, to 3 from 0.5. You can keep it all the way down to the surface of the cylinder, however the graph will look very weird and it may be hard to read. So for you guys, I will leave it at 0.5. Okay. So this will be the velocity variation in viscid flow. So this is where you want to specify that is at start of cylinder at the middle of cylinder at end of the cylinder. Okay. And then we'll change this to velocity u, and this one should just be y. Okay, that looks good. So we'll take a screenshot of that. Okay. So now we want to exit out chart view, and we want to create a contour. This first contour would be from symmetry 1, and we will do velocity with 110 contours. Okay, so that looks really good. I'll zoom in there so you can see better. As you can see, it creates an area of low velocity right after the cylinder, and also a point of very high velocity. Also, you can notice the point of very low velocity in front of the cylinder as the velocity is basically stopped at that point. Okay. Okay. I'm going to exit out of that, and it's important you exit out of that, otherwise the result will just be on top of each other. Symmetry 1, 110 contours, this would be the pressure contour. Okay, that looks good. Exit out of that, and now we will enter the streamline. 250 points. We want to start from symmetry 1. All of this should be good. Okay, that looks very good. Okay. Okay. And then let's try. Okay, yeah, that's the only one to try. Okay, that will be all for the inviscid flow.